Director of the Energy Systems Engineering Program.
Hey, good evening, everybody. This is our first of our series of distinguished lecture series, and we are really honored to have Dr. Donahue, Neil Donahue. I heard him speak about a couple of months ago, and I think you're going to enjoy this presentation. Again, just to give you administratively how we're going to do this, he's going to speak for an hour or some, more than an hour, and then we'll have Q&A, and the show will be over at 7:30. So here's a brief description of Neil's background. He's a Thomas Lord Professor of Chemistry in the Department of Chemistry, Chemical Engineering, and Engineering and Public Policy at Carnegie Mellon University, where he's been on the faculty since 2000. He's the founding director for the Center of Atmospheric Particle Studies at CMU. He's now the director of the Steinbrenner Institute for Environmental Education and Research. He represents all environmental research education at CMU. And he's also a Pittsburgh native, so it's very appropriate that he was born in that city, and now he's working there. He has a bachelor's from Brown University and a doctorate from meteorology from MIT. He has shown that organic materials is very dynamic with compounds condensing to and evaporating from the condensed phase frequently during their roughly 1-week residence time in the atmosphere, all the while undergoing oxidation chemistry. So anyway, Dr. Donahue.
Thanks for the invitation, Rudy. I really look forward to speaking. We have a decent amount of time here. I hope I won't talk for a full hour. Also, since you have surveys and your pencils hovering over them, I feel a little bit of pressure. Maybe you could have clickers and the score going up and down, and we can see how it's going. But yeah, so what I'm going to talk about today is actually mostly not my own personal research, though I have some of that in there because I can't really avoid it. And also I want to say that I'm happy to start, since we've got till 7:30, if you've got questions, if I'm saying something that isn't clear, if you just don't think you agree with the graph I'm showing or whatever, just stop me and we'll talk about it. I can even jump off and give a different talk on different stuff because I like to do that. So we'll make it where we need to get, and the more interactive we are, the better we are. I've got a clock over there. That's the only one I've got, so we're good to go. All right, so I am a climate scientist, and these are interesting times to be a climate scientist. And this is a Far Side cartoon from many, many years ago, and that's about how I feel sometimes these days. So it's become odd, but. What I'm going to essentially skip over, and I can give several presentations on this, is the world's getting hotter, and the reason is because of us. Okay? We actually understand that very, very well. And again, I could go into the details, but this is a summary of the global average, the change in the global average surface temperature of the planet, which means nothing, but it's basically everything. In degrees centigrade since about 1900. And it's about a degree warmer than it was in 1900. And we know that reasonably well. There's many, many self-consistent data sets that go into this record. And year to year the temperature goes up and down, but the big maroon swath there is the contribution of human activity to that change. And we understand the other contributors as well, and again I could go into that, but the other contributors generate all of the variability, and the maroon swath with the green trace on top of it is mostly from fossil carbon dioxide, but it has some other contributions as well, which is where I'm actually going to start. This is the starting point. We understand the fundamental physics of climate change. They're pretty straightforward. I could get them to you in about 15 minutes if you wanted to. And we see the signal, we see the data, the rate of increase is about what we would expect, what we do expect from theory. It's what we've observed in what we call paleoclimate if we go back to the ice ages. It's an incredibly consistent story. This is a real thing, it's being caused by us, And the question really is, what are we going to do about it? So this increase in temperature is the result of what we call a climate forcing. So the simplest way to put it is we break the climate problem up into two bits. And the first bit is the forcing. How hard are we pushing on the climate system? And we measure that as power. We measure that as watts per square meter of surface area of the planet. It's how much extra heat is coming to the surface. This is what we call surface forcing. And then the second part of the system of the problem is, okay, now that I'm pushing on the system harder, how far does it move? How much warmer does it get? And it's about 1 degree warmer now. And so this, the forcing part, is measured in watts per square meter, and we've added a couple of watts per every square meter around the surface of the planet. It's like a Christmas light bulb on a Christmas tree, every square meter over the entire surface of the planet. So it's not that big a forcing. It's not that big a temperature change compared to 300 degrees absolute Kelvin, but it matters. So now I'm going to break this forcing down, and this is since about 1980 again. And there's a little forcing roughly up until the time I was born, and then everything kind of goes south or north. So you can kind of blame it on me. So since approximately 1960, that forcing has increased dramatically. I've already said it's mostly fossil carbon dioxide, but it's not entirely carbon dioxide. So I'm going to break it all down here. Here's a function of time. And I'm going to start with something that's actually a cooling. And the cooling is the fact that when we burn stuff, we add carbon dioxide to the atmosphere, but we also typically generate smoke. We generate particles, they make haze, and that aerosol haze is hard to see through. It's hard for the sun to see down through as well. It scatters light back into space. And that cools the planet because that's solar energy that's not absorbed. So that's a cooling effect. And especially in recent decades, that cooling from aerosol haze that we call direct scattering of sunlight is fairly strong. It also happens to kill about 4 million people on the planet per year, and I'm going to get to that. And that the cause of that, the sources of those aerosols and their health effects and their climate effects is the central research that we do at Carnegie Mellon in the Center for Atmospheric Particle Studies, where strangely enough we study atmospheric particles. And those are the particles we're interested in. So now the second effect of this overall global warming is a cooling. Okay. A cooling effect, and this cooling effect is also from particles, but it's what we call the indirect effect of particles on climate. And so this is through what we call aerosol cloud interactions. About 60% of the Earth is covered by clouds at any given time. About half the light shining on the top of the clouds typically makes it down to the surface. It doesn't go dark when a cloud goes overhead. But so on average, about 30% of sunlight is scattered back into space, and most of that is off of clouds. So they're puffy and white, but they don't scatter all the light that hits them. And it turns out that the whiteness, the brightness, how much light clouds can scatter, it's called their albedo, depends on how many droplets are in the cloud. If I took a cloud, and I took all the water in a cloud, and I made it into one enormous swimming pool-sized drop, first of all, it would be terrifying. You'd have a couple of seconds to realize what was going to hit you, and that would be it. Right? I mean, the swimming pool heading down. But secondly, you could see through a pool, right? The light refracts some, but you can see through. If I take the same light and I turn it into a spray, into a nice fine mist of 10 nanometer droplets, which is what a cloud is, then it's white. So it's the surface area on all those droplets that scatters the light in the end. It's many, 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 many bits of refraction that scatter the light. So the bottom line is that if I have the same amount of water, but I have more droplets, I got a whiter cloud. And cloud droplets all form with the assistance of a particle. Every single one of them. If you didn't have particles in the atmosphere, you could supersaturate air to 300% relative humidity. But we have particles in the atmosphere, and so you only get to 100.5% relative humidity, and then bang, you get a cloud. So every droplet forms on a particle. That means if I have polluted air with more particles in it, when the air rises up and cools down and reaches what we call the lifting condensation level, remember I'm a meteorologist, then get a cloud, but the number of droplets depends on the number of aerosol particles, and the polluted air will produce a cloud that has more droplets, which makes it whiter. And so we've had more pollution over the past several decades especially, and the clouds are whiter. The snow over Pittsburgh may have been gray, but the clouds over Pittsburgh were noticeably whiter. Pittsburgh's now quite a clean place. But just as here in Bethlehem, the still city used to be a very polluted place to live. Trust me, I grew up there. Okay, so that's two effects, two coolings. The next effect that I'm going to add on to that baseline, so this green trace is going to show the sum of all of these effects as I kind of add them together. This is the warming effect associated with fossil carbon dioxide. And again, this is extremely well understood physics. It absorbs infrared light. The details are kind of interesting, but that's not part of this talk either. And so that now overwhelms the cooling effect. And now we have a net warming over the past 100 years. And that's the largest single thing in this whole story by a lot. So CO2 alone is now causing warming, but we're not up to the total yet. We've also increased the concentration of methane in the Earth's atmosphere for a series of reasons, agriculture and fossil methane extraction over the past, actually thousands of years, but mostly over the past several decades as well. Methane is an extremely strong greenhouse gas for various reasons, and so that adds warming as well. In addition, we used to, nitrous oxide, N2O, it's not just for laughing gas anymore in dentistry. It's actually always emitted from soils. So when you fertilize, fertilizer has an extremely strong embedded warming. It's actually one of the policy issues associated with climate science is that we make fertilizer through the Haber-Bosch process. Right? So you take the agricultural revolution was essentially fueled by hot copper catalyst. You take nitrogen and methane and you heat them up in a pressurized system that Fritz Haber in Karlsruhe developed in the 1920s, and you get ammonia. So you break the N triple bond and you reduce the nitrogen to ammonia. And the ammonia then is the basis for fertilizer, for ammonium nitrate. So every molecule, every mole of ammonium nitrate that you put on a field when you're fertilizing actually came from natural gas, from methane. And the carbon in that at the end of the process goes into the atmosphere. So every ammonia actually is a CO2. And that's part of the carbon emissions, but it's a significant issue when we think about climate policy. So when you add, this is all a bit of a diversion on that, the nitrous oxide there. When you put ammonia on soil, some of it in the nitrogen fixation process, there's a small amount that's converted into N2O. Nitrous oxide is also a strong greenhouse gas, and it's extremely long-lived in the atmosphere. Its fate is to go up into the stratosphere where it dissociates and contributes to ozone depletion, which is another whole talk I could give. But because it's long-lived, it's also, and because we've increased the amount of fertilizer we're putting on soils, N2O emissions are increasing, concentration is rising, and again, it's a greenhouse gas. I haven't emphasized this yet, but all of these forcings are changes. So the question is, how much did the energy balance change from a fixed reference time to the present day? And the fixed reference time in the climate story is typically the pre-industrial, and by definition it's 1750. So we're interested in changes since 1750, but most of these have taken place since the Second World War around the world. Okay, we're not there yet. So the next thing, speaking of stratospheric ozone, chlorofluorocarbons, halocarbons are also extremely strong greenhouse gases. They're very strong dipole moments. They absorb infrared light extremely well. And once again, they're extremely long-lived. That's why they're very useful as refrigerants and foaming agents and everything else. Unfortunately, when they get into the stratosphere, they photodissociate, and the chlorine catalyzes ozone destruction, and so we don't emit them anymore, which is a good thing from the climate perspective as well, since it started since about 1990 in the Montreal Protocol. and various amendments to it, global emissions of chlorofluorocarbons have essentially stopped. They're extremely long-lived. They have about a 100-year lifetime in the atmosphere, and so the concentration hasn't started to go down much. So the contribution of Freon to global warming kept going up until 1990, and now it's constant. We're getting there. The last thing on this list is, in addition to everything else, I just spoke about ozone depletion, there's what we call good ozone and bad ozone. Ozone up in the ozone layer in the stratosphere absorbs ultraviolet light and does lots of good things for us. If you make ozone down in the lower atmosphere, it's a strong oxidant and irritant. It damages crops and people. We call that bad ozone or ozone pollution. And ozone concentrations down here at the surface have increased significantly since 1900. 10 to 20 parts per billion from some early electrochemical measurements in Paris in 1890, and now in many parts of the northern hemisphere where we hover in the 40, 50 parts per billion range all the time, and so ozone in the lower atmosphere is the last of the greenhouse gases. So you add all that together, and you get this overall effect. Most of these things, fossil carbon, methane, the implicit nitrous oxide, when you work your way back, is basically the Haber-Bosch process, have to do with combustion. And that's mostly fossil fuel combustion. And even these cooling effects from these dashed lines here have to do with combustion and the emission of aerosols. So when you put it all together, we understand well the total forcing caused by human activity. I can also split it this way. All the warming effects on the positive side of the ledger, and then the cooling effects on the negative side, and the sum there in that red and white trace. And so actually, when you look at it this way, the aerosol effects and all that other stuff I just talked about, the methane and the nitrous oxide and blah, 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 kind of cancel each other out, and at the end of the day, the total warming forcing is pretty similar to the forcing from carbon dioxide. So CO2 is not only by far the largest single thing in this whole set, but the other stuff kind of cancels out more or less. So it really is a story of carbon dioxide. Now, it's not perfectly certain. Current times especially make me need to be a little emphatic about our understanding. We do understand this well, but as a scientist we tend to go in the other direction and emphasize what we don't understand. And I do want to be very clear about degree of knowledge and certainty. So each of these contributions has uncertainty associated with it. And so we got the grays are coolings, and the various colors from red to green are warming. And I'm going to take those, and so you see there's 3 watts of warming there and about -1 watt of cooling there. And there's our reds through greens and 3 watts of warming summed up. And that's our best guess, but this is a probability distribution where there's a 95% estimated certainty that it's within this range, and it's 3 1/4 plus or minus 3/4 of a watt or so. And that's actually a very, very high degree of confidence. This is a very narrow distribution function. We understand the physics of transfer of infrared light through the atmosphere extremely well. These are all very long-lived gases that we can measure extremely well, and we have good records of their concentration dating back, in many cases, millions of years, but certainly through the industrial era. So we understand that this warming part of the story with a high, high, high degree of certainty. And the fact that these are all extremely long-lived gases is going to come up again and again. So that's the warming part. The cooling part is different. Again, especially because the forcing is by definition how much the energy balance has changed from the pre-industrial to the present day. In order to understand the aerosol cooling effect, I need to know how much the aerosol concentration has changed from 1850, or even 1950, or 1750, excuse me, or 1850 or 1950 to the present day. And that's hard, because all of these long-lived stable gases, as I said, we have very good records of, with the possible exception of ozone. for hundreds of years. You can find them in ice cores. There's all sorts of ways to get those paleo data. But we can't go back and count particles. Actually, there's this latent project I have. I want to go, or send somebody to go through the logbooks of the British Navy from the Napoleonic Wars, because visibility is a proxy for aerosol concentrations. That's this whole cooling effect, right? Light can't go through aerosols very well. And if there's one thing that sailors in the crow's nest were really good at, it was spotting French frigates. Right? So there are records of distance of sightings of known ships with known mast heights from 1792 until 1815. And it would be kind of interesting other times, but that's when there happened to be lots of frigates zipping around the Mediterranean. And so it would be kind of interesting to get a record of visibility from records like that. But we don't understand this very well. So by far the largest uncertainty, when you add these two things together, the sum, the uncertainty, you add them in quadrature and all those things, right? So the uncertainty here dominates the uncertainty here. And the bottom line is that we don't actually know how hard we're pushing on the climate system all that well. We know it's getting hotter. And we know that we're pushing on the system reasonably hard. But it's actually, there's a factor of 2 range in just how hard we're pushing, easily. And that's a problem. And it's a problem that we're working to solve. And so for that reason, understanding the aerosol effect on climate has been a major motivation for a lot of the research that we do. Okay, so let's talk about particle sum. One of the, let's go back here for a second. So these, the direct effect, the scattering of light is mostly, it relates to the total mass of particles reasonably well. It really relates to their circumference, because that's how they interact with light. But that's not, that's scales reasonably with the mass. But the aerosol indirect effect, the cloud seeding effect, depends on a number of particles that are in the air mass making up the cloud. And counting numbers of particles historically is especially difficult. The whole exercise I just described in going back to the Napoleonic logbooks wouldn't work. They weren't counting numbers of particles at all. So that indirect effect is where the largest amount of uncertainty is. And so we need to understand, essentially from first principles, what leads to number of particles in the atmosphere. And the thing that dominates the number of particles in the atmosphere is a process we call nucleation, formation of particles from condensable vapors like sulfuric acid and other extremely low vapor pressure compounds that get formed via atmospheric chemistry, supersaturated. It's the inverse effect of whipping a cork off of a bottle of champagne, and then you nucleate bubbles because the partial pressure of carbon dioxide went down in the water, in the headspace above the champagne. Well, here we're generating molecules via gas phase chemistry. They really want to be in the particle phase, and so when they bump into each other, they make a new particle. That process is what we seek to understand. It's called nucleation. And I like to say I do particle physics at CERN, but when and we just sent a bunch of instruments out to this experiment last week, the particle physicists I know look a little puzzled because my particles are a couple of nanometers in size and extremely low energy. We're not looking for Higgs bosons, but this is the Large Hadron Collider at CERN. Actually, there's not a white line on the ground. The Geneva Airport is there, and we work on a little accelerator that is the warm-up track to the warm-up track to the Large Hadron Collider, as they have to get the elementary particles up to speed, basically, to inject them into the LHC, into the big ring. And so it's called the proton synchrotron, and it was the accelerator during the 60s. And the reason we use it is that the beamline, a beamline in the proton synchrotron produces energetic particles that are a reasonable mimic for cosmic rays that come into the atmosphere from outer space. And those cosmic rays generate secondary ions as they streak through the atmosphere. And those ions are a great way to start the formation of particles. So one of the many uncertainties in the story is the contribution of ionizing radiation, cosmic rays. Actually at the surface, radon is another contributor to that. to the ultimate formation of new particles. So we can do it in what we call neutral, just make a molecule, they stick together, or it can be ion-assisted, where I make a little cluster of an ion, usually with water around it, and some particles stick to that little cluster. So we call that ion-induced nucleation. We want to be able to separate those out, and so the CERN setup is a great way to do that, and that's the cloud experiment, as we call it, at CERN. So we study the physics that leads to new particle formation it's the cleanest 26 cubic meters on the planet, literally, at atmospheric pressure. So we can take the concentrations of everything down to extremely low levels. It's surrounded by a whole series of mass spectrometers and other things that can measure the particles and their composition, and then ratchet up the concentrations step by step, using actually a lot of what I'm interested in as a chemist is a lot of the chemistry that produces these compounds is new to science, and it's really cool and interesting. We also control the temperature. It's wrapped in insulation, so we can scan the temperature through the ranges of temperatures that are found in the atmosphere. And I won't go through many details about that, but we measure formation rates of particles, nucleation rates of 1.7 nanometer little clusters with about, they have about 20 molecules in them at that point. This is a function of the concentration of things that we call highly oxygenated organic molecules, homes. But they're compounds that get produced with many, many oxygens. They're very, very polar, and they stick together very well with each other. And as their concentrations increase, the nucleation rate also rises. The lower curve is under neutral conditions. The upper curve is when we have effectively cosmic rays in the system. That enhances the nucleation rate by up to a couple orders of magnitude in that case. And system by system, we've been working through the chemistry and physics that can produce particles so that we can implement, these particular molecules in this case are alpha pinene oxidation products that come from pine trees. So it's a natural source of precursors for these nucleation vapors. Most nucleation in the present day involves sulfuric acid, which almost exclusively comes from oxidation of SO2 from coal combustion. So most sulfuric acid in the present atmosphere is due to human activity. Alpha pinene is not, other than the fact that we've changed forests. My colleagues in Finland make a lot of measurements in the boreal forest where there's Scots pines produce a lot of alpha pinene, so it's kind of a favorite molecule of ours. But basically system by system where the emissions will have been either perturbed by human activity or not. If we understand the particle formation rate, we can begin to try to model the formation of particles in the pre-industrial and the present day, and therefore understand the change in that aerosol effect. And so when we do something like that, this is from a paper that appeared in the Proceedings of the National Academy of Sciences last year. This is a model simulation, a global model simulation of the total cooling associated with particles. So comparing the present day to the pre-industrial, and the blues are colder, and you basically see that in the northern hemisphere there's been a cooling from aerosols because that's where people are. And it's about minus 0.6 watts, which is right about in the center of the range from the estimated effect that I showed you earlier. I mean, these estimations do come from someone. There's pretty good agreement about that. But when we add in this pre-industrial source of new particle formation from oxidation of biogenic alpha pinene, it slightly reduces that cooling by about 0.2 of a watt. Quite a significant amount, not an enormous amount. We haven't said, oh my gosh, climate change isn't happening. But this is, that we have to work our way very, very carefully through these processes. A little personal note here. By the way, oh my gosh, climate change isn't happening because there's formation of particles from biogenic oxidation. That is the conclusion that the Wall Street Journal drew from this work. And we actually knew they would do that. It wasn't this paper, but it was this paper. That appeared in Nature in May of last year, along with a companion paper that describes the growth rate of those particles. And the then Republican presidential candidate proceeded to give a talk on energy. These appeared in the 3rd week of May. And by the last week of May, it was actually one of the few times he stuck to the teleprompter. They actually implicitly were quoting this result because it had been summarized in the Wall Street Journal as scientists at CERN show that that aerosols from natural sources drive climate change, basically, which is actually not what we concluded, but the word from this sort of stuff can show up rather quickly in the common conversation. And as I say, we were aware that that might happen, but this is what we were working on. So we see that we slightly reduce the total amount of estimated cooling associated with aerosols. The overall, I should point out, the overall math here is a little complicated because we know it's getting warmer, right? And so the more cooling, the particles are hiding some of the warming. The more cooling there is from aerosols, the more warming is being hidden, basically. The less hard we're pushing on the system, and it is getting hotter. And so if we infer how sensitive the system is to changes in forcing, the more cooling that's out there, the less pushing we're doing, the less total warming we're exerting on the system. That means it's more and more and more and more sensitive. So when we find that there's less cooling, it means that we're pushing a little harder maybe than we thought we were. So it means the climate system is somewhat less sensitive to changes in forcing than it would be without this effect. Thus the conclusion that showed up in the bottom line editorial that there's not as much warming as we thought there was. Actually, there's just exactly as much warming as we thought there was. It's just a question of how sensitive the system is to a given amount of forcing. Okay, so particles are hiding some of that cooling. That's the research that I'm personally intimately involved with. Let's go back to the CO2 side of the story, because the single, if you come out of this talk with one fact, if I can make one point that you remember, carbon dioxide lasts forever. It is unlike, yes?
So how long do the particles last in the atmosphere? And the reason I'm asking is because if you stop polluting right now, and particles came out quicker than CO2, it would get hotter.
Boy, is that a good question. The particles last a week.
Oh.
So when it rains, they're gone. Okay? With one exception. If you get the particles into the stratosphere, if you're a volcano, or if you're a person who wants to put aerosols in the stratosphere to generate cooling, which geoengineering. A friend of mine, David Keith, actually gave a talk 2 days ago at CMU on that. And I can talk more about that afterwards. So basically, stratospheric particles last for 2 years. Tropospheric particles, because they're removed by rain. Remember all the cloud stuff I was talking about? At any given place, it rains about once a week. And so the residence time of particles is basically a week. So as soon as you stop emitting them, they're gone. And even 2 years is short in this business. So if you blow them into the stratosphere, it takes a couple of years for them to settle out of the stratosphere and then get pulled out by rain. That's why when you geoengineer, you put them in the stratosphere, because they last 100 times longer than if you put them in the troposphere. And they get dispersed, and nobody breathes them, and they might destroy some ozone, which is one of the problems. But all aerosols are short-lived, and almost all of the greenhouse forcers are long-lived. But CO2 is the prize winner here in terms of a persistent pollutant. And so this is how I'm going to illustrate it. And the reason basically is that CO2 equilibrates between the atmosphere and the ocean, like that bottle of champagne. It's a highly buffered system though, so when we add carbon dioxide, effectively about half of it goes into the ocean relatively quickly, and the rest, due to the buffering, can't really go anywhere. And about a quarter of the total emissions, which is about half of what we ever see in the atmosphere, doesn't go away until we add weathered mountains to the ocean to make limestone. And it takes 100,000 years. So it sticks around in the system basically forever. And so this is a set of emission scenarios using a model that I got from a friend of mine, Ralph Keeling. And Ralph's father is fairly famous as the guy who started to measure carbon dioxide in the atmosphere in 1958 at Mauna Loa. And so these are the emissions of carbon dioxide in billions of tons of carbon. I'm a chemist, I count the carbon, I count moles. The oxygen's free, it comes on from combustion from the atmosphere, but the carbon's what we care about. We're presently emitting about 10 billion tons of carbon every year as carbon dioxide. That's a really big number. We just worked out in a freshman seminar class I'm teaching that we generate about 1 million tons of people per year. In other words, the production so here's the math, right? There's I don't know, 10 billion people on the planet. We live for 100 years. Those are both wrong. But so there's basically 10 divided by 100. That's 100 million births per year. We make 100 million people per year, basically. And we'll call a little person about 10 kilograms. So that means that it's 1,000 babies is a ton. a ton of toddlers. So 1,000. So that 10. I'm trying to do the math too fast, but it works out to 1 million tons of babies a year. Oh, I set my computer to sleep. And whereas we produce 10 billion tons of carbon as carbon dioxide, this number dwarfs all of the other fluxes in the whole human system. It's just an immensely big number. And these are the concentrations of carbon dioxide, the Keeling curve as measured since 1958. The first data point on this graph is 1950, and the pre-industrial value is right about here at 280 parts per million. So those are the emissions, those are the concentrations, and if we put in a relatively simple model that has all the essential physics of where carbon dioxide goes in the atmosphere and ocean, by the way, biosphere uptake on average is a very small number. We're cutting down trees in the Amazon, but CO2 is going in other places, and it all balances out. It's about 10% of this whole story. So one thing we could do over the next 150 years is just keep burning stuff. There is plenty of fossil carbon out there. One place, if you're interested, is ice hydrates in the ocean. Thousands of tons, thousands of gigatons of carbon, thousands of gigatons of carbon in methane hydrates in the ocean. There's many other places. So we can do that. If we want to pursue global development by burning coal and methane, we can do it. There's nothing outside, and that's basically the high industrial scenario in the IPCC report, just simplified a little bit. If we do that, that's what the carbon dioxide concentration will go. It will continue to accelerate, and we will pass, by the end of this century, we'll be above 750 parts per million of CO2. And even the short-term climate response, every 100 is about a degree. And we'll get that warming. If instead we froze emissions at the current 10 billion tons per year, which is actually a fairly drastic action. We do that. Seems like a big difference between red and magenta. The CO2 will do that. Because the CO2 is essentially immortal. If we keep emitting at the same rate, the concentration of CO2 keeps rising at the same rate. And yes, there is some ocean uptake, and so yes, you'll be seeing it rolls over a little bit. But that's a fairly small perturbation. So if we keep emitting carbon dioxide at the same rate that we're doing it now, the concentration will continue to rise. Again, it is immortal. That is the one thing I want you to take away. It means that in this conversation, if we want to stop an increase of carbon dioxide in the atmosphere, we must make net emissions go down. Mind you, from the atmospheric perspective, all I'm saying is you can't put the stuff in the atmosphere. And by the way, you can take it out of the atmosphere, but as a chemical engineer, I would much rather get carbon dioxide out of the stream that has 10% CO2 in it than something that's got 400 parts per million in it. I'd rather have the thermodynamics in my favor than opposing. It's a very hard separation problem to suck it out of the air. But it can be done. It's a relatively straightforward separation problem to get it out of a flue. It's done at industrial scale all the time. So all I'm saying is we cannot emit carbon dioxide into the air if we don't want the concentration to go up. So if we decrease global emissions of carbon dioxide at a couple % per year, which is what that green curve shows, then the CO2 concentrations will look like that. And remember, this is about a degree, and this is the short term. There's another ½ degree or so of inertia in the system, maybe a little bit less, a quarter to a ½ degree, as we warm the ocean. So what's called the equilibrium climate response is greater than we've seen so far. And there's climate response hiding behind the particles. So if we do the 2% reduction, then we will hit a scenario where the actual concentration rolls over, and again, there is ocean uptake, so there'll be some leveling off of that. Of course, at the same time, the deep ocean will have warmed up, and so that longer-term sensitivity actually roughly cancels out, and we'll see essentially constant increased temperature if we decarbonize. And finally, because I'm a scientist, I can imagine a scenario where I say, right now, we're done. But as a practical person, it's irrelevant, but it's useful to see what the CO2 would do. And I find this useful because actually the green and the blue aren't all that different. So if you imagine policy scenarios that ultimately result in a couple % reduction in CO2 emissions per year around the globe, that's not all that different from a catastrophic shutdown right now. So let's forget about the catastrophic shutdown part and begin to think about policy solutions that decrease emissions at a modest rate. Globally, that includes development and everything else, a couple % per year, actually basically gets you where you need to go. All right, that's the CO2 part. Oh, by the way, it keeps going forever. So if you want to do planning out to 2500, again, CO2 is immortal. It sticks around forever, and that is the one point I want you to take away from the talk. So I've hammered that one about 7 times now. That is the unique element of carbon in the climate story from a policy perspective. Back to the particles, and that's where I will wind up, and then we can have questions. They do kill people. So, and it happens that the same actions are producing fossil carbon are also producing fine particles as air pollution. Not entirely, some of this comes from burning wood, but most of it, or agricultural refuse mostly, almost all of the bad air in Beijing comes from some form of combustion and some industry, some cars, a surprisingly large amount from cars. That's the Forbidden City. That's a bad day on the left. This is a so-called blue sky day on the right, but there's mountains in the background. My niece lives in Beijing at the moment, so I take this one personally. And air quality in Beijing is pretty bad. It's as bad as it was in Pittsburgh in 1950 when Pittsburgh was held with the lid off. In fact, it's probably a little bit worse. So the fact that the sources of fine particles and carbon dioxide are co-joined means several things. It means that as we reduce carbon dioxide emissions, we are very likely to reduce that cooling associated with particles. Okay, you win some, you lose some. But it also means that we will reduce the pollution associated with those particles. And what I want to close with is to try to convince you that that's a really big deal. It's a clear and present, well, it's a very hazy and present and local danger. So what I'm going to show you now is some work from some colleagues of ours who are members of a large EPA-funded center that remains funded at Carnegie Mellon to look at aerosol and health effects. And we're looking at very, very, very fine resolution measurements around Pittsburgh and elsewhere to try to study the epidemiology of these aerosol effects at the block scale. Does it matter if I live next to a restaurant, et cetera, et cetera? Really, we see particles coming out of a wonderful Argentinian barbecue restaurant called Gaucho and other things. We like the food in Gaucho, but we don't like the emissions very much. So So what I'm going to show here, this is some work from a guy, Michael Brower, and his colleagues, Josh Apte, who's at UT Austin. And what I'll show is, so you know, like Beijing, we know from satellite measurements and some modeling and a few different sources, we have a reasonable idea what the aerosol concentrations are at pretty high resolution around the globe. And we know how many people live in every 36 by 36 kilometers square that we can draw around the globe. And we know roughly what the health response, what we call the dose response from particles to people is. And I should say that we actually understand reasonably well why particles kill people. And particles are responsible for 3 of the top 10 sources of mortality around the globe. It's not a first world problem, it's not just a third world problem, it's a big deal everywhere. Essentially, when you breathe in, particles deposit in the little particles smaller than about 2.5 microns in diameter, they're small enough so that they don't have too much inertia. A big particle, if I breathe in and I make it turn a corner in my nose, it'll slam into my nose. And so pollen, when you breathe in through your nose, gets lodged in your nose, and if you're allergic, that kind of sucks. But it doesn't get into your deep lung. And an allergic reaction is, for the most part, just annoying. The little ones, when you breathe in, they go all the way into the deep lung, and some of them settle in the alveoli. And when they do, the body's response, especially when it's a particle, is inflammatory. So the kind of local physiological response to, you know, a 100 nanometer particle's got 1 million molecules in it, some of which have oxidants, and there's some relatively unhelpful compounds that are generated in that chemistry that I was describing that leads to particle formation. And so you overwhelm the local response of the cells that have this bolus of stuff land on them. And so the body responds with increased cytokine levels. It induces what we call systemic inflammation. And if you want to have a heart attack, you need 2 things. You need high cholesterol, but that alone won't kill you. If you have systemic inflammation, that triggers the response in the body that leads to atherosclerotic buildup, hardening of the arteries, and ultimately an infarction, a heart attack. And so the ultimate cause of mortality from fine particles is largely, there's also a cancer response, because the 3 sources of death having to do with breathing in fine particles are breathing. Breathing over a 3-stone cooking fire, largely in the developing world, which is mostly women and children in enclosed spaces in kitchen cooking areas, and breathing through a lit tube of tobacco. The health effects are actually all the same. So, and they're all about the same in the end. Smoking is much worse for you than breathing polluted air, but not everybody smokes, and last time I checked, everybody breathes. So in the end, it kind of washes out. Okay, so what I'm going to show you here is the exposure on an annual average basis of people to fine particle air pollution. This is a logarithmic axis here. So we measure fine particles, we weigh them, so we measure their concentration in millionths of a gram, micrograms per cubic meter. It's a really small number. Cubic meter of air weighs 1 kilogram. So a millionth of a gram in a cubic meter is 1 in a billion by mass. And we care about that number. So at 10 in a billion, this is the World Health Organization goal for air quality. The US National Ambient Air Quality Standard for fine particles is 12 parts per million. So you're out of attainment if your concentration is bigger than this. And these are a bunch of intermediate goals here. So what I'm going to show you is a population distribution put on top of this. So we'll start with China. So by a population distribution, if you add this up and you work on the axis, the integral of this number, it's the visual integral, what you see there is about 1 billion people. And what this is saying is the modal concentration, the modal exposure in China is about 65, 70 micrograms per cubic meter. This is Beijing. This is probably Beijing, this is probably Shanghai, that's probably Guangzhou. The concentrations basically go high in the north down to somewhat lower as you head down into the Pearl River Delta. But pretty much everybody is in the 50 to 100 microgram per cubic meter range. Air quality throughout eastern China is very, very bad. And there's very high exposure. So that's 1 billion people, most of whom are exposed to concentrations on an annual average. When I started in this game, the daily standard in the United States was here. And that's the annual average above it. So then we'll add on India and other mostly South Asian countries here. India, the air quality in the Indo-Gangetic Plain is every bit as bad as it is in northeastern China. You get to southern India and it's better. But there's very high pollution levels as well. So that's another billion people, and then Bangladesh, Pakistan, Nigeria slid in there, Indonesia across here. And then I can add in the Western Europe and the United States. So we've gone through a development cycle. I keep referring to the Still City, to Pittsburgh back in the day, being over here. And so the sort of standard development cycle has been to get over here, say, oh, this isn't so nice, and then work on post-cleanup. And we've gotten ourselves over here. So there's been an incredible benefit to air quality cleanup over the past years, and I'll show you some figures on that before I wrap up. And so in the US and Western Europe, there's still exposure. Our standards here, so most people, many people are still exposed to what we would call unhealthful air, but we're a lot better off. And then finally, the rest of the world. So that's the entire population of the planet and what people are exposed to on average. That's the exposure. We know the dose response reasonably well, though it's another area we continue to work on also in more detail. And so I can turn this exposure into mortality. Or I can, Josh can. So again, that's the exposure. This is worse for you than this. So when I look at deaths, at excess deaths, this moves, and you see the emphasis here. Right? So when you add it all up, this is about 4 million premature deaths every year. And it's heart attacks, right? So it's easy to think, oh yeah, there are 4 million people who died today who would have died next week. No, it's actually not so. So you can also, another of the measures of in health, in the World Health Community, they call them disability-adjusted life years, DALYs, which take into consideration sort of lost years of life and productivity. And the story is essentially the same. So it really doesn't change that much because it's an affliction that sort of works or occurs in otherwise healthy people as well as more vulnerable older people. And so there's essentially 1 million deaths per year in China. The Chinese government gets it, so there are very intensive measures being taken to improve air quality in China. It's just about as bad in India. That's another 500,000 or more deaths per year. But that number there, I mean, it looks small, but it's 100,000. So there are 100,000 deaths in the United States every year from breathing excess levels of fine particles. So it matters here too. And as I begin to wind up, I'm going to wind this back to the local scale and us in Pennsylvania. And the policy implications, I won't get into this much more, but are I said it's a clear and present or hazy and present danger. Since the sources of carbon dioxide along the climate forcers and this air pollution are the same thing, you get people's attention when you talk about killing people locally now. And you get people's attention for good reason. 4 million deaths a year is pretty catastrophic. 100,000 deaths per year, by the way, is more than traffic accidents, it's more than opioids, it's more than a bunch of real calamities that are getting justifiable attention in the present day. So yeah, let's wind back to us. There's us within this distribution. And wind back to some of the work that's behind some of this estimation. And this is what's called a meta-analysis that was put together by one of the actually the original paper on air quality, on aerosols and mortality, was published by an economist at Carnegie Mellon University, Lester Labe, in 1970 in Science. But it was so much before its time that, except for a few people, almost nobody noticed. And then various studies in the late 80s, most famously the Harvard Six Cities study, actually brought it to attention when there was more epidemiological data. And one of the guys behind the Six Cities study was a fellow, C. Arden Pope. And I can tell you many stories about Arden, but he's one of the members of this center that we have at CMU as well. And so this figure here is looking at life expectancy in 51 municipal areas across the United States. And again, the same kind of axis here, right? So exposure, PM 2.5 exposure. It's a linear axis now. And the 50 municipal areas are there. Sometimes I have a black and gold circle, but I didn't put the black and gold on it this time. In this, and around 1980, the most polluted city in the United States had an average exposure of 30 micrograms per cubic meter, and 3 rivers and barely functioning steel industry. And the least polluted had about 10 micrograms per cubic meter. And the y-axis there is life expectancy. Correlation is not causality, but in this case, this actually, a lot of this is causal. Okay? So the cleaner cities, people are living in 1980 fully 2.5 years longer. And that relationship, basically every 10 micrograms per cubic meter improves life expectancy by about a year, is the same number that comes out of now hundreds of this sort of study all around the world. Essentially, 10 microgram per cubic meter increases your risk of mortality by about 1% or 2. It's actually closer to 2% at the end of the day. And then go to 80 or 90 micrograms per cubic meter, that's fairly alarming. And the risk actually does roll off a little bit. So they went back in 2000, so 20 years later, the Clean Air Act had taken effect, actually for 2 main reasons. We didn't like smog, we didn't like ozone. So we put catalytic converters on cars, and we were told that our cars would get more expensive. Yes, they did, that's the whole point. If you're an economist, you're internalizing the environmental cost of the pollution. They didn't get very much more expensive, it's about $100. It costs more to put a new one on your car, but the OEM cost for a catalytic converter is about $100. And people get buying cars, right? They cost a little more, but the sales, the auto industry didn't change. So we did that, and also we didn't like acid rain. And so we put sulfur scrubbers on power plants. We did not have a standard for fine particles at that point in time. But by the year 2000, there were no cities left above 20 micrograms per cubic meter. We were down to 5 in some cities. My favorite black and gold city, if I had it on here, would be near the sort of bottom third, but not right at the end of the distribution. The same life expectancy relationship from 1980 I've reproduced here, and essentially the same slope holds, but the data are much more compact, so there's higher statistical uncertainty in that fit, but that actually is a fit to the trend line there. And this is the current National Ambient Air Quality Standard. But again, I emphasize, actually, this air quality improvement preceded the air quality standard. It was a co-benefit to other actions. And when you work it out, and people are living longer, about 20% of that improvement in life expectancy over that 20-year period was attributable to that. That's a very big deal. So of order 25,000 lives per year are being saved by that air quality intervention. And the Clean Air Act is through multiple economic studies, one of the most cost-effective pieces of legislation that was certainly in the public health sphere ever written. So they're saving our lives. And finally, I'll conclude with this one. So when you take this information and you say, yeah, gosh, we don't, you know, there are reasons why we might want to not emit fossil carbon dioxide, but energy policy and everything is the subject of your center here. But, you know, wind power and solar energy is a good thing. We like them. We do. Where are you going to put photovoltaics in the U.S.? What's a good place to site photovoltaics?
Mojave Desert.
Mojave Desert. Sun's always shining, right? You even got sand there, so if you want to make a plant and you, that would be fine. But yeah, the Mojave Desert's a beautiful. How about wind?
Offshore.
Offshore's nice. There's already a lot of it in Texas. Northern Great Plains, NGP's got a lot of steady wind. Great place to site wind farms, right? What are we going to displace? Yeah? There will be habitat effects, yep. But also, what power is it going to? You know, if I'm going to add wind, if I'm going to add solar production, presumably I'm going to remove some production as well. We could have said the Sierras as well for some of that wind.
Just going to meet increasing demand, not necessarily going to displace.
That's also and there's some base load considerations and a bunch of other interesting things. But let's assume for the moment I can displace, at least within an interconnect, some power. If I consider the health effects, it turns out, and this is from a PhD student in our Department of Engineering and Public Policy, Tyler Seller-Evans, by far the best place to site solar is where the coal is. Right? So if you include the social cost of, which is estimated to be about, I think it's about $30. So this is the health benefits per kilowatt of mostly it's PM 2.5. It's almost entirely PM 2.5. But the social cost of the coal combustion is $25 or $30 a ton. Basically, that's a ton of CO2 emissions. And so when you work it out, so there's essentially no coal combustion in the Southwest. And so if you stick with it, we don't have very good long-range transmission right now, right? That's actually a key problem. If you like high voltage DC or something like that, you can begin to think about actually moving electrons over a long distance. But as long as you can't do that, then the siting economics actually speak heavily in favor of putting, they give a large advantage to non-polluting sources of energy in places that have high population density, that have current sources of electricity that are very polluting. And if you can figure out a way to fold that social cost into the rate structure and the governance, you get a very different picture about where you want to put the power sources. And with that, I'm done. Thank you for your attention.
All right, must be a lot of questions. Fascinating talk.
Yes?
I have a question. It's not completely, it's not directly related to your talk specifically, but it's just something I wanted a little bit more clarification on. Because, there's a ton of information out there concerning this topic, and sometimes it's hard to weed through what's the science and what's the politics.
Yep.
So when someone says 97% of climate scientists agree about climate change and its effects, what exactly are they referring to?
They're referring to, if you look through, and there's actually a science historian named Naomi Oreskes actually did the study of this. And so she went through, in the study was in about 2005, I think. They went through papers published on climate, having anything to do with climate change, basically, in the peer-reviewed literature. And they looked for references that had anything to do with not attributable to human activity, basically. And there's essentially nothing there. That's where the 97% come from.
Now, what implications does that have for, consequences to coastal cities, or, so trying to separate the adverse effects from the simple fact that the humans are clearly influencing the climate.
Right, what's actually going to happen? Why do we care? As a simple scaling number, so if we go to the peak of the last ice age, the last glaciation, the Earth was about 6 degrees cooler than it is today. So when you think about these global average temperature numbers, I'm not suggesting we're going to be covered in ice because we're going the other direction, right? But in terms of the meteorological response to that degree of warming, 5 or 6 degrees is essentially a glaciation. It's essentially an ice age. So when we talk about 2.5 degrees of warming, we're talking about the equivalent of half an ice age change in meteorology. And so you see large changes in regional rainfall patterns and precip minus evaporation, which is what we actually care about, which is soil moisture. You see large increases in extreme events, and so heavy rain, etc., goes up, and that's a robust result from climate models that gets more. David just showed that David Keith, the guy I was talking about, who's looking at geoengineering. Higher resolution climate models, where we model circulation at finer and finer scale, are now doing a pretty good job of representing hurricanes and also representing precipitation statistics. So when you run them for a long time, one of the ground truths is you say, does it statistically produce a world that kind of looks like the present day meteorology? And the answer is, yeah, it does a pretty good job. And when you look at those out to the future, what you see is, it's a little oversimplified, but dry places get drier and wet places get wetter, and you see more extreme precipitation. So it's very likely that that sort of effect would occur. Agricultural zones move poleward. If you're Canadian, that might be a thing. If you're a farmer in the central United States, it might be less good. The other thing out there is, he's talking about coastal cities, the most robust thing is the sea's going up. Well, the temperature's going up, the sea's going up. And it's going up for two reasons. One is you make water warm, it actually expands a little bit. And most of the sea level rise that is discussed quantitatively in the summaries, such as the IPCC report, are that. Thermal expansion of the ocean is related to sort of millimeter per year kind of increases in sea level. Which doesn't sound like a lot, but that's a meter per century, and the rates are many of that, several of that. And that will happen. If it gets warmer, see, it just has to happen. The sea's got to expand some, because we understand the thermal expansion of water. My history is one of stratospheric ozone, and there's a little bit of an aside, but I'm not pivoting on your question. The ozone hole was an example of a large-scale surprise in the bad direction. None of our understanding of the science in the 1970s included the chemistry that resulted in rapid ozone loss over the Antarctic. And I could go into a lot of detail about what actually causes it, but we didn't predict it. We did predict the sort of more steady reduction in ozone over the equatorial and mid-latitude stratosphere that we have in fact observed. But all the attention that in the end focused on that big enormous hole over the Antarctic. And so we worry about, I mean, that's an example where things were a lot worse than we were predicting. And the concern there would be Greenland, right? So when you look at melting of continental ice sheets, you can get, so you melt Greenland, you get 7 meters. And you melt the, which one is it? The West Antarctic ice sheet, you get another 7 meters. And the East Antarctic ice sheet ain't going anywhere. But the thing is, so Greenland will melt. There has, if we go to a 2 degree warmer scenario, if we go to 450, 500 parts per million of carbon dioxide, there is no time in the geological record when there was ice in Greenland when we had that much carbon dioxide in the atmosphere. And so it's almost certainly going to melt. And the question is, how long is it going to take? Right? If Greenland melts and we get 7 meters of sea level rise over a millennium, it's reasonable that we can kind of run away from it. If it melts faster, it gets a little bit more concerning. And we don't really understand the mechanics and the physics of glacial behavior, ice sheet behavior that well. So there will be increased sea level. There already is So we talk about storm surges and that's a real effect. And we've already seen it. And then the future kind of surprise thing would be faster ice sheet melting. So I hope that helps.
Yeah, thank you.
Yes?
You mentioned Haber Bosch and making fertilizers.
Yeah.
And, using methane to do that, and I guess the carbon from the methane goes in the atmosphere. CO2, right?
Correct.
How about the coal that's burned to heat the stuff? What matters more? The chemistry or the heating?
Oh, so the chemist, actually the methane, that's a good question. I mean, you get, so how many, I said it was 1 to 1. I gotta work that out.
I mean, you're heating the stuff too.
It's a high temperature process. Yeah, it's a high temperature process.
Right.
It is not exothermic to turn N2 into ammonia.
Right. So it's even more than.
So yeah, you actually do add. Yeah. Yeah, I don't know the answer.
And while you're at it, how about making cement?
So making cement, I didn't put. Making cement is actually, if you look at, I'll show that. I've actually had my freshman seminar making these graphs just today. If I break down. That was the pre-industrial. That's the one we just looked at. Where'd it go? Here it is. This is also an answer to the, is the carbon dioxide increasing because of us? Yes. So these are the contributions to CO2 that we have here, the global burden in billions of tons. This is that same trace from Mauna Loa. Carbon dioxide is very well mixed in the atmosphere, so we just happened to start measuring in Hawaii. This is the contribution from coal combustion, from oil combustion. So basically, before the Second World War, we burned coal, pretty much exclusively. The automobile took off after the Second World War. That's the contribution from petroleum. Natural gas is obviously a source of fossil carbon. And so this is the CO2 from methane combustion. It's not the methane contribution that I showed before, which is the methane itself, but when it's burned, it turns into CO2. And that one there is cement. So cement is, I mean, that's actually not a tiny source, but it's a couple percent. Yeah.
So you were talking about clearly rising sea levels as one of the problems. So it's the main, one of the urgent climatic effects of global warming. And with that, of course, there will be displacement, and so people will be forced to migrate and relocate to other parts of the world. And with also, but as that's going on, there's also going to be population growth, because human population will overgrows at an exponential rate. So essentially, you're going to be having a lot of people going into finding the mainlands. Everyone's going to be congested into these small cities and simultaneously growing exponentially. So it seems almost like a trajectory that could never really be reversed. Is there some sort of plan to mitigate is there some sort of most of the plans to mitigate climate change really never really don't account for this this population growth? Is there some sort of analysis that shows how much this will how much of a role this will play in creating solutions for this for a much greener future?
Yeah, and so I'm a humble climate scientist, and so the sort of global development part, what's in there? Nuts. So I was looking for some figures I have that I am personally not, here we go. Let me get that talk. Do it again. Oh, well, I'll just talk about it. So, from the perspective of climate forcing, the story to date is much more of a resource than a population. So, essentially all CO2 emissions to date have come from the US, Western Europe, and now China, basically. And so even if you factor in economic development in China and India, and economic development in the developing world, but that will be in terms of energy intensification. The way I think about it is a simple equation where you have population times energy use per person times, or it's, you put 4 terms in there. You've got population, you've got prosperity, GDP per person. Then you have, the way we get prosperity is by basically using energy. So you factor that all in, but you get, then you finally get to how many tons of carbon do we emit per watt. And so on the future side, there are a lot of scenarios you can make that say, I can find that there are plenty of sources of low carbon energy. So you can do global development with non-fossil sources of energy. That is a solvable problem. You are going to get climate change, and you are going to get social upheaval associated with that, yes. And the sea level rise one is just one of the wild cards of the problem. But Shanghai is very close to the ocean, and many other cities are too. So it's a balance.
So the burning of a carbon fuel on its own is, if that was mitigated, the effect of the growing population would really not overtake the already existing problem.
That's what I'm arguing. Yes, that if you as a global, in fact, this is not with my climate scientist hat on. This is sort of my climate activist hat on, if you will. The connection between development and climate is they're sometimes painted in opposition, and I think that's a tragic flaw. And so the issue of anyone talking seriously about climate change mitigation has to, on the policy side, talk about energy development and global development. Those cannot be separated. But it is a solvable problem. We do happen to need low carbon sources of energy, but we know how to do that. And the precedent is, I talk about the kind of the tried and true scenario behind here where we burn stuff, we make a lot of pollution, we realize we're killing everybody, and then we kind of back off and figure out how to have some end-of-pipe solutions. That's the same thing as saying, all right, I want to get teleconnections, so I'm going to string a lot of copper wire. We don't do that anymore. You put up a cell tower, right? In the past 20 years, we've seen development solutions that are very different, and it so happens that those also use energy in different ways. We're making a lot of devices that really like DC, low voltage, now. And so the idea that we can develop globally in ways that are not strong sources of fossil carbon, I don't think that's a fantasy. And I think we really have to connect. Yeah?
After 9/11, when all the planes were down and people were talking about
Yeah.
is that just don't know, is that like still a valid idea? Does it matter? How much does it matter? The vapor trails of airplanes actually come down.
Yeah, we.
I'm asking because I want to feel better about flying around.
Yeah, I fly 150,000 miles a year, so I worry about the CO2 emissions. You didn't say chemtrails, but so just look up chemtrails on the web, and you'll feel my pain. We don't emit weird stuff in the atmosphere from airplanes, but that's part of it. But the contribution from airplane contrails is actually quite small. And yes, I was one of the people who looked up on, we had a seminar visitor on 9/11, and wow, airplanes. I wonder what that's going to do to the contrails. And the study was done. But most of the global dimming, I mean, is where's Beijing again? It's not an airplane. So a colleague of mine in the Wilson School at Princeton, Louis Mazerow, has a paper appearing where they look, I mean, this is a very significant effect on solar photovoltaic potential. It's a real deal. But conversely, so if you're putting in PV in the JJJ, in the Beijing area, and you look at what are some of the co-benefits of cleaning up the air, one of them is that your photovoltaic potential goes up by like 30%. It's a very big, it actually changes the diffuse and direct light and all sorts of interesting things. Any more?
So, let me ask you a question.
Okay.
So now that, I know policy is not purely driven by technology, we can't hope for that.
Yeah.
But if we had to have like a list of to-dos here, what would take precedence? Shut down the power plant, drive less, be more energy conscious, and if we were to switch over to a renewable portfolio, then we also need to tolerate less reliable electricity. So are these, what would you think would be the most important things to do, see the throttle back CO2 emissions?
So the good old conservation is, so getting the wonky way to say conservation is I talked about dollars per watt economically. If you look at the relationship between GDP or gross net income or whatever in energy use, there's a strong relationship. And we use 10 kilowatts per person, and we have the highest prosperity, basically. And that's highest energy use, too. But there's a spread of a factor, too. So average energy use in Europe is about 5 kilowatts per person in the 5 or so most developed countries in Europe. And it's not just because it's more compact. That answer is actually wrong. It's because the energy use is significantly more efficient in Europe. And so more efficiently generating prosperity from energy. And by the way, gasoline is 3 times more expensive as well. So everyone uses trains that are electrified. And so that would be the first best quick fix is probably pricing incentives that also encourage more efficient use of energy. For generating prosperity, not just putting on a sweater in the moral equivalent of war and all of those tried and true statements from the energy crisis. That would be one. Yeah, I mean, cutting down coal and appropriately internalizing it. And there's, even without internalizing the environmental consequences of the pollution, it's not clear that the coal combustion is going to stick around much longer anyway. It's kind of going by itself. But that would send it on the way. So, internalizing that. If I were king, $30 a ton per year, rising for 20 years, carbon tax.
Well, thanks a lot, Neil. And token of our appreciation, we have
That was a wonderful talk. So on behalf of both Energy Institute and everyone else here, I'd like to see you.
Thank you.
Very much. So,
thank you, everybody. So,
Thank you.
we meet a month from now. We'll have a
Beautiful.
similar lecture series. And then you.
I want to use this.
that way we don't do anything. Just drink it away.
Yeah.
There's still like a little sign-up.